This section is going to be about algorithms and macros, and honestly, I almost didn't include this, but I thought someone out there is going to ask, so why not just put it in? We've already talked about QDeleteAll, but I want to go back to familiar territory and talk about this very briefly, just in case anybody skipped the previous videos. What is this? Well, C++ requires us to manage pointers, and what QDeleteAll does is delete those pointers out of a container, because remember, QObject cannot be copied. We have to work with pointers. Point in case, pun intended, haha, I know, we have this test class here, which very, very simply just is going to tell us it was constructed and deconstructed. We want to see that life cycle in memory. So let's go ahead and say QList. We're going to work with our test class. Of course, we have to work with a pointer because we cannot copy a QObject. And I'm going to keep this very short because we've done this a few times already. And let's just say I want to make 10 of these. And let's go by increments. And from here, of course, we're going to do something very, very bad. I'm going to make a pointer. And I'm not going to use a smart pointer. I'm just going to say, you know what? I just want to do it this way. Now, again, I did cover this in the previous section on memory management, but notice no parent, no automatic smart memory pointer. I shouldn't say auto because auto is a keyword in C++, but you get it. There is no smart pointer here. We are 100% flying at the risk that the developer knows what they're doing. Let's go ahead and set the object name, and let's go ahead and call this QString number representation of I. And then we're just going to list.append. And let's go ahead and put that object in there. Now, what this does is a few things. A, we now have a container filled with pointers that we have to manage. And this can get a little bit bad, meaning we can introduce all sorts of bugs into our application. Let's go and say at 0, just so we can list this out. Now, if I save and run this, what have we really done? Well, we've created a memory leak, meaning we've constructed all these pointers, but they're not being deleted. Most modern operating systems, when I close this, is going to wipe that for us, but don't count on that. That's not always the way things work. Remember, the beautiful thing about Qt is it runs just about anywhere, so you're going to run into just about every imaginable solution. We need to be able to delete those pointers out of the container, and instead of doing a for loop and deleting them all at once, we're just going to say Q, and we want delete all. And then we simply hand it our container, and it does its magic. But you'll notice if we try to do something like this again, it's going to crash. And there's a reason for that. We've now created another situation called a dangling pointer, where we have a pointer, but it doesn't point to a valid object because it's been deleted. Let's go ahead and demonstrate this. So now you see how we've constructed, and then we have deconstructed because we called that QDeleteAll, but when we try to access it, we crash our program. Okay, that's one of the major takeaways here, is you should make sure you always, always, always clear the container. And never try to access them because it will crash it. Once you called QDeleteAll, you should consider this right here actually gone. And what you're going to want to do from there is make sure you don't have any objects in there at all. So we can say something like QInfo. And we can just simply call count. And let's demonstrate this super quick. See, we have 0 in there. I'm going to improve this just slightly. And I want to demonstrate something very fundamental, just in case you did skip the other videos. We're going to go right after delete all, and we're going to do this count. You're going to see these objects are still there, even though they've been deleted. And to kind of clarify that on the screen, save, run, and let's see this in action here. So we've called QDeleteAll, but we still have 10 items. That's why we have to clear that out. Let's talk about filling a container with values. We want to do this because we want to, well, populate a container. This is actually a pretty common thing. We used to use qfill, but it's deprecated. So now we can just simply use qlist because it's built right in now, or the standard library. Let's go ahead and give a standard example here. So normally you would do something like this, where you make a qlist and then you start pushing values into it. Well, we don't want to do that. We just want to fill a list out. Normally we would say qfill, and if we try to use that, notice what's happening. Use of undeclared identifier qfill. This is actually in the older compatibility module, but I don't want to cover that because I don't want you to rely on this. Instead, we're just going to say, no, this is bad, don't do this. Do not use. So instead, we're simply going to say list.fill. It's baked right in now, so there's really no point in trying to make it harder than what it really is. And let's go ahead and say qinfo this out. And let's go ahead and save and run and see what this looks like here. So what qlist_fill is going to do is, you guessed it, it's going to take from 0 to the maximum number. We put 4 items. It's going to fill each one of those with the value we specified. Now, that being said, somebody out there is going to go, well, how do I change the count? Well, you would just simply say resize and set it to whatever value you want. In this case, I'm just going to say 12. And then someone else is going to say, well, how do I use the standard library? So we're going to say std fill. And let's go ahead and say list.begin to list.end. And let's say we want to fill this in with -1. You may be asking yourself, why are there multiple ways of doing this? What happened to qfill? Well, you're going to run into this time and time again with the newer versions of Qt, where they start deprecating things because when this was first created, fill wasn't even in qlist, and the standard library really wasn't up to the task of what they wanted. So they kind of built their own. And I think at some level they kind of went crazy and went a little overboard. But point being, now they're starting to rely more on the standard library or baking it right into the classes. And you can see both methods work really, really easily. Which is the one you should use? Well, it depends on your needs. If you're used to the standard library, by all means, use the standard library. If you want to use, you guessed it, the fill function, feel free. Just simply do not rely on the old way of doing it because it's deprecated. Let's take a look at how to sort a container. Now, this is something we used to rely on qsort, but of course it's deprecated. Well, we can use the standard library, and I'm just going to show you how to do that, even though I'm assuming you know C++, this may not be abundantly obvious to everybody. So let's go ahead and let's make a function. We're going to call this randoms. It's going to take a qlist of ints, and let's call that list with a max amount. And we're just going to make some random numbers. This is the beautiful thing here. We're just going to make some random garbage and then try to sort it out. And I'm going to reserve the maximum amount. And then for int I equals I is less than max. You may be wondering why I did a reserve right at the very beginning here. So if I highlight that and hit F1, it attempts to allocate the memory for at least size elements. So I know that I'm going to add a certain number. Why not just reserve the memory up front rather than having a minor memory increase as you're trying to add them? Now, that's changed slightly in some of the behavior in the newer versions of Qt, but I wanted to really highlight that. If you need to make sure you have the memory, you just call reserve. We're going to say int value equals, and let's go ahead and make a random value here. We're going to say q random generator. We want the global and bounded, which is going to give us between 0 and the highest number. Is it 0 or 1? Let's find out. I'm pretty sure it was between 0. Okay, it generates one between 0, inclusive, and the highest value. Got a little concerned there, like, oh no, I know I need some more coffee, but did I forget that? So we're going to say list.append, and let's go ahead and add that value. Now, this is what I'm talking about, the difference between reserve and append. If we highlight append, inserts a value at the end of the list. This is the same as calling resize. So every time we append, we're going to resize. Ooh, that could be bad, right? So if you really want the performance, go ahead and reserve it up front. That way you're not resizing every single call. Not really going to see a performance benefit in this small little application here, but in bigger applications, you will probably notice some sort of difference, even if it's minor. Again, I have to take credit for Qt because it runs just about everywhere on big beefy desktops. Unless you're working with massive lists, you're really not going to notice. But if you're working on like some small little device where memory is very constrained, you'll definitely notice a difference. And I'm just going to say 10. Like I said, this little app, not going to make a difference. So all we're doing here is we're making a Q list of ints, and we're going to throw it into our randoms. We're going to say we want 10 items into this list. It's going to do its magic. From here, we have an unsorted list. So let's just print that out, see what it looks like. It's going to be random every single time, just to kind of add to the complexity here. You know, 23, 836, you kind of see they're all over the place here. Now, in the past, we would simply call Q sort. Now, you notice it's still trying to do that. Don't use Q sort. Q sort's bad. It's bad because it's no longer going to be supported. So instead, use the standard library sort. Got a little ahead of myself there. List begin and list dot end. And that's going to sort it the correct way. Now that we've sorted it, somebody out there is going to say, now, wait a minute, how do I sort it the opposite way? Like if you've ever been in, say, a spreadsheet program, you can sort ascending and sort descending. Well, it's already baked into the standard library, so there's really no reason to reinvent the wheel here. We're just going to say reverse, and then, of course, list dot begin and list dot end. There's really two fundamental concepts I'm trying to drive home here. First is that over time, Qt has deprecated things that have been either added or improved in the standard library. And you can 100% work with Qt and the standard library. They work very, very well together. So let's go ahead and save and run and see what this looks like here. So without further ado, unsorted is just a really big mess. Sorted, of course, starts with the smallest, goes to the biggest, and then reverse goes from the biggest to the smallest. Again, this is not rocket science, but you'd be surprised how many times I get asked, well, how do I integrate Qt with the standard library? They both run on C++, so it's just right there for you to use. And another one would be Q equal. It is also deprecated. I'm adding these in because people coming from Qt 5 are going to go, what happened to Qfill, Qsort, Q equal? They're all deprecated. I'm just simply showing you the standard way of doing it. Again, name self-explanatory. We just want to ensure equality, or I should say check for equality. Standard library comes in and says, hey, I can do this. So we have our little function here that just creates random numbers inside of a list up to a certain maximum. And we're already using this. So we're saying we got list 1, list 2. They're going to be just random numbers. Let's just save and run, demonstrate what this is going to look like. We have 2 totally random lists. It's not likely these are going to even remotely match. But let's just say we were getting those from, say, a library or something. We would want to know if they're equal using Q equal. And you see that Qt has no idea what we're even talking about because it's not there anymore. You'd have to use the algorithms, and we don't want to go there. But just in case you're curious, this is about what it would look like. you would say QInfo equal, Q equal, and then you'd have list begin, so on and so on. Now, what we can do is modify that. So I'm going to grab this. And let's instead say std equal. And then we have list1 begin to list1 end to list2 begin. So you see what's going on here. We're saying grab this list, list1, and check it against list2 starting at this position. And that's what it's going to print out is, hey, is it equal or is it not equal? Go ahead and save and run. It is not equal for obvious reasons. Now, let's just modify these lists real quick. Let's go ahead and fill list 1 with number 9, and let's go ahead and fill list 2 with number 9 as well. That way we know, very painfully obvious, they're equal, but we just want to check and test this thing out just to make sure it works as advertised. Sure enough, they are now equal. Now, I know on the screen they look different. It's just because we simply didn't print those out. Just in case we really gotta see all the details, because somebody out there is going to say, well, wait a minute, it was different on the screen. Let's just print them out. Save, run, take any of the mysticism out of this. So sure enough, they're now equal. So let's look at something that, well, is pretty standard. A lot of people do this. You have two lists, you want to copy one into another. We used to use qcopy, but of course now that's deprecated as well. We're going to use the standard library. Again, we have our random function, which is just going to take a list and fill it with, well, random numbers. That being said, let's take a look at this. I've got list 1, we're going to fill with randoms, and list 2 that has nothing in it. Let's go ahead, save, run, and see what this looks like. So list 1's got stuff, list 2 does not. We need to figure out a quick and dirty way of copying in there. It's actually very simple. So I'm going to say QInfo. I'm just going to say copy. And let's say list 2, resize. And we're going to do the same size as list 1. Because they're going to be equal when we're done with them. And we're going to say standard library, and we want to copy. And we're going to copy from the beginning to the end. And then we need to tell it where in list 2 to actually start copying. So I'm going to say list 2 at the beginning. You could have actually set a different position, but that's what we're going to do. And then we want to validate that these are actually equal. So I'm going to kind of combine our previous talk about equality. I want to say QInfo. I'm going to say std equal. And then, of course, we just simply have the same API. So I want to say, grab this. We're going to make sure that from list 1 begin to list 1 end, and we're going to start at list 2. We just simply want to see these things. And plop that in, we're good to go. Go ahead, save, run, and watch it in action. All right, so we've got two different lists. We're going to copy them, and we're going to make sure they are equal, and we can display them on the screen, and everything works as expected. Again, I'm really just adding these in because somebody out there is going to say, what happened to this specific function? In this case, qcopy. How do I copy these over? And they may not even understand that this is built right into the standard library. Another question I'm often asked is, how do we make our own custom macro? This really isn't a cute thing. This is a C++ thing, but you know, why not? Let's just throw it in here. So let's go ahead and we're going to make a custom macro. We're going to define add And we're going to say add A and B, which of course is going to, in the return, going to say A plus B. Notice what this is and what this is not. It is a preprocessor directive. It is not straight C++ code, meaning this is not a function that we're actually writing. This is just simply a macro. But we can interact with it through our code. And yes, I did overly simplify that just for the sake of explanation. There's a lot more to macros under the hood. Let's go ahead and say easy, but dangerous, as I'm about to explain. So let's go ahead and say QInfo. And we're going to add 1 and 2. What do you think is going to happen here? If I save and run, we get number 3. So it is working, and it works as expected. But of course, we are going to live dangerously. Let's break it. So I'm going to just copy and paste. Already got these queued up. A whole bunch of stuff, and we're going to uncomment these and run them. So we know this works. Now let's try to take a string and an int. Notice how it's saying warning. It's not saying error, it's saying warning. Bad things could happen. But let's run it and see what happens here. Okay, it just gives me this. Why did it give me that? That's a good question. It's saying qbyte array view h. So it's actually giving me the header file to say, hey, you know what? I really don't know what you're doing. What are you thinking? Okay, well, let's uncomment this one. We're going to take true and true, see what happens here. We get 2. Okay, interesting. All right. You think it would just be true, but, you know, not how computers think. Let's take false and true and see what happens here. We get 1. So those of you that are computer experts know what's going on, but really there's no type checking under the hood here. And we can end up with some really bad things. If we really, really wanted to, we could really crash this program. And that's why I tend to stay away from macros. As we kind of thumb through these, you can see some of these things are going to work as expected, while some will just simply not. So for example, this one, let's run this and see what it does. What happened? We took this and that and added it, but it printed nothing out. That's the official sound effect of this video, is the it did nothing. It says adding char to a string does not append to the string. So basically we just wiped that whole string clean. Not fun. Undesired behavior. And then let's do this and see what it does. Same thing. So when in doubt, yes, macros are at your disposal, but I tend to avoid them for the reasons we just outlined. The behavior may not always be what you're expecting. And by the time you start adding in all the logic, you might as well just make a function to begin with and get it over. The big benefit here is if you're using a C++ function, you have type checking and all those other things in there, and it just works way, way better. One thing that really doesn't fit anywhere else, so I just decided to put it in this section, is typedef. I'm assuming you know this. I'm assuming you've worked with it before. We've even covered it in some videos, but I always get questions about typedef. It really allows you to make your own data types. And if you're still very confused, think of it more as an alias, meaning let's work with QMAP. We want to make a very complex QMAP in terms of typing. What I mean by that is, let's say QMAP to string, comma, int. Now you may not think that's super complex, but when you're typing away, you don't want to type that hundreds and hundreds and hundreds of times. So we're just going to call that people. And in front of this, I'm going to say type def. What did we just do? Oh my gosh, basically type definition, type def, we're going to turn this into the alias people. So now we can just grab this guy and work with it directly as a data type. Now there's a lot, again, I'm overly simplifying just for the sake of explaining this. There's a lot of things that happen in the background, but really now people is a type def or an alias towards this. So we don't have to type that all over again. The big problem with type defs, they're confusing Because if you're just given this code here, where's people? Where did it come from? Is it a class? Oh, you hover over it and you see it's this. And then you're like, well, wait a minute. Why didn't they just say that? And some APIs will go absolutely crazy with typedefs to the point it will drive you insane. Windows API, for example. Anyways, point being, don't go crazy on typedefs. No one likes them. Your code should be very descriptive and very easy to understand just by looking at it. And that is the conundrum, is typedef is really designed to make your code easier to understand. But if you use it too much, it's going to make your code much harder to understand. So there's a fine line between using it and overusing it. And to be brutally honest, professionals have struggled with that fine line. I'm going to say for each auto key in p.keys. And then let's print this out. I've been happily typing away while I was talking. So you can do some really funky things like this. Now, just looking at this code without being able to mouse over, how do you know what people is? Is it a class? Is there other functions? What's going on here? But because we know QMap, it makes it a little easier. So I'm going to beg you, if you're going to use typedefs, please use them very, very sparingly. And when you use them, make sure it makes sense to use them. You'd be surprised some of the code I've reviewed where there are typedefs for everything. It's ridiculous. I made this video because I'm asked quite a bit, which should I use? Should I use Qt? Should I use Boost? Or should I use the standard library? Well, let's just consider this gray box as an application. And we're going to look at some case studies here. This first example, it's not one or the other, it's all of them combined. You can absolutely use Qt with Boost and the standard library. If you have no idea what Boost is, it's boost.io out on the web. Huge, I mean, massive set of free code that you can just download and use, and it works on top of the standard library. Unfortunately, when you start intermixing one library, say Qt, with another, Boost, you might run into some issues because they both try to accomplish the same things and they start bumping into each other. So this is actually pretty standard of some bigger, I want to say, enterprise applications. And then you'll see people do something like this, where they just use Qt and they use a standard library. We've kind of represented that in this course. And this is perfectly fine. Because remember, under the hood, Qt is also using the standard library. And then you'll see people do this, where they'll just use Qt and nothing else. And that's also perfectly fine. So the question becomes, which one should you actually use? Well, it depends, right? Boost and other third-party libraries have a ton of functionality baked into them. And admittedly, sometimes Qt falls short and you do have to interface with a third-party library. And that's fine, as long as you follow their documentation. So whenever somebody comes to me and says, hey, I downloaded this library and I can't get it to work with Qt, my first response is, please contact the author of that library. I don't know their API or their code. And then it's on you to kind of figure out how to interop between all of them. If you split your application into Qt and the standard library, typically what people do is if you have some sort of business logic you may take with you to other frameworks, other libraries, things of that nature, leave it in the standard library. And then use Qt for Qt things. Like, for example, if you're going to do sockets, or if you want to use Qt for the file operations, threading, concurrency, timers, things like that. And then you'll have people like me who just like, you know what, this code is going to live in Qt forever. I have no desire to port it anywhere else, so I just write it all using Qt. Let's take a look at something that's vastly confusing to most people, but it's actually Computers 101. Most courses don't even really touch on this. Let's make it very simple. So here we have memory, and in here we have PIDs. What are PIDs? Process IDs. These are different processes. So what's a process? Well, it's a running copy of the executable. So when you make a program, that program can be executed multiple times. Each process consumes CPU, RAM, disk space, things of that nature. And most of them are, well, little islands amongst themselves. They don't even know the others exist. If you take a process and zoom in on it, you're going to get something like this. where a process, even if it's a self-contained static compilation where everything's supposed to be all in one and people think are super cool because it has no dependencies, it still looks like this. It's a process making system calls to other parts of, well, code, libraries, and even other processes. So a process could call a library, which calls a library, which calls a library, and so on and so on. You can have multiple libraries all over the place. And then you have a process talking to a process. This could be multi-processing, sub-processing, a number of different ways of doing this. This could be a communication through a network channel or something like that, or shared memory. Point being, this can get very, very complex. But usually it looks something like this, where most processes don't even have a clue the others exist. So let's just take a look at this. Whatever system you're on, I'm on a Linux box. Click whatever is the representation of the system button down here. I think it's the start button in Windows. And type in the word system. And you're going to look for something like a system monitor or process monitor. You may be able to hit Control Tab or Control Delete, and it will bring open like a task manager or a process monitor. You're going to get some representation of like this, regardless of what operating system you're on, where there's going to be a process name. This is the actual executable, whom or what executed it, how much CPU it's using, the ID, the memory that it's using, and then some of these task managers will actually show you like how much disk you're using and things like that, and then a priority. This is the priority in the CPU. Now everybody's going to go, how do I make mine high priority? Don't. Let the operating system do what the operating system does. But point being, this section is all about examining processes. And as you can see, just on this little virtual machine, there are a lot of them, and most of them don't even know the others exist. So for example, let's just say this CSD color probably has no clue what this NM applet is. They just don't know about each other. They don't need to. But sometimes, just sometimes, you want to be able to communicate between processes. Now, a typical workflow is going to look something like this. The operating system is going to start your process, and there'll be some parameters or information exchanged so the process knows where it's starting and what startup variables it really has. But you may perform some work, and you may send that to another process. This is actually very, very complex under the hood, but Qt makes it very simple. Once your process has finished, you're going to have an exit code which tells the operating system what happened. The standard exit code is 0, which means nothing to see here, no problem. But it looks like this. Operating system starts your process does some work and may talk to another process, and eventually when it stops, there's an exit code and the operating system knows how that exited, whether there was no problem or there was a specific error code it needs to examine. This video really represents how a process communicates. So if you wanted to send data to a process, you could send it through the standard input, through a socket, dbus, file stream, or other, like a memory map file or something like that. The process would then do some work, and then it would output either a standard output, standard error, it could be a socket connection dbus file or other, meaning this can get very complex very fast, and we're not even going to remotely touch on all of that. Specifically, what we're going to really be looking at is standard input, standard output, and standard error. This is how a lot of processes work under the hood. They talk to other processes through standard input, standard output, and standard error. Once in a while, they do talk to each other through sockets or some other means. We have a fundamental problem here. Qt can run just about anywhere, but how do we know where we're actually running? For example, I'm running on a virtual machine using Linux Mint. You may be on Mac or Windows or something entirely different. So we want to be able to look at the OS details, and we don't want to dive into specific OS APIs because, let's face it, that's just horrible. We're going to use qsysinfo. It's actually very simple and very straightforward, so I'm just going to copy and paste because it's really that straightforward. We're going to say qsysinfo, sys, and then from here, I'm just going to info some stuff out, and you can see we can get the system info, boot ID, build, kernel, version, and then I put this little note here in case you're coming from Qt 5. Sys Mac version and Sys Windows version has been replaced with product version. And of course, we have the machine host name. That's actually the name of the machine this is running on, the pretty product name, and the product type. Let's go ahead and save run. This is what you're going to get. We got the boot ID, we have the build, CPU, the kernel. Of course, I'm running Linux. You may see like Windows, Mac, whatever. You have a version and you have a host, and the product is the pretty product name. This is something like you would display in an about box. And then we have a type, Linux Mint, and then version. So this is actually very informative. There's a lot to this little class here. Most of the time, what you're going to be looking for is, hey, what am I running on? Or what is the pretty product name for some about box or something like that? Or do I need to check if there's a specific CPU type? Now, that being said, this class really is that simple. But now that we know what we're running on, we may want to run code for specific operating systems. For example, I may want to say on Windows run this, on Mac run that, and on Linux run something else. And that is also ridiculously simple. So I'm going to paste this in, and we have some definitions. You notice how it's grayed out down here. There's a reason for that. Your QoS underscore is only defined for the operating system you're on. So it's defined on Linux. But if I go down here, you'll notice this QoS Win32. It's simply not defined. It's not triggering anything. If I highlight it and hit F1, you'll see, yes, defined on 32-bit and 64-bit versions of Windows. Okay. But there's also Windows 64 and QoS Win. So if we wanted to, we could actually shorten this to QoS Win. And then we have QoS Mac and also unknown. Anything that starts with Q underscore OS underscore is going to be a definition for an operating system. And there's a lot of them in there. For example, and I'm not going to go through them all, but AIX Android, BSD4, Darwin, CGWin, HP Unix, iOS, Linux, Mac OS, on and on and on. I mean, they try to really let you know what's going on here. But what's going on for us is if it's defined, it will run this code. However, if I was on Windows, this would be grayed out and it would run the Windows code. Mac, the others will be grayed out and the Mac code will run, and everything else would run this unknown OS code here. Let's go ahead and save and run and see this in action. See, Linux code here. It's not going to even attempt to run the Windows, Mac, or unknown code because it's simply not defined. Remember, when in doubt, it's Q underscore OS underscore and then the operating system. Let's actually use a process now. Why? Because why reinvent the wheel? There are tons of applications already on your operating system, and you can simply install more if you need them. So we need to interact with those using QProcess. Now, QProcess is a little complex, but in a sense, it's basically like opening a command line, typing a command, and having the operating system run it. There's more to it. I'm overly simplifying it, but it's kind of the same thing. So we have some code here. We're going to say if test compress with gzip, else fail to use gzip. Gzip is a compression utility. That being said, this will strike fear into the heart of a newbie programmer because they're like, oh no, I need to go find the gzip header file and learn about compression. Why? Why reinvent the wheel? Just call the existing process and let it do what it's going to do. So I'm going to say QProcess gzip, and you'd honestly be surprised how many applications actually do this under the hood. Gzip.start. So what are we doing here? Well, we're making a QProcess. Give it any name you want, but then we're going to go ahead and start it. This is just like saying, hey, command line, go do something. And we're going to start the gzip application. We're also going to use some start parameters here. So I'm going to say q string list -c. Now, if you're not on Linux, don't despair. You can still follow along and do this. Just change the name of an executable and change any startup parameters you want. You could do like notepad.exe or whatever you want. You'll actually see it starting. This is assuming we're using a command line application, and I know that Notepad's not a command line application. But so let's grab gzip here. And it's just, what we're doing is basically this. We're going to say gzip-c, and then bang. And we have to give it some compressed data too. So we're going to actually use standard input, standard output. Now, how did I know -c? Because you got to read the documentation for that app. That's the major pitfall here, is that no one who writes software does it in a standardized manner. So you have to read their help file and figure out how to work with it. So now we need to wait for that to start. And this is a little confusing because a lot of people are like, what do you mean wait? Let me go ahead and fill this out and let's explain it here. So we're going to say if not gzip dot wait for started. And notice you can time that out. Wait a number of seconds, use milliseconds, of course. What's going on here is we're saying, hey, operating system, go run this. And if you don't have it in your environmental path, meaning you can't just type the name, you'll have to give it the full path. Then the operating system is going to go out to the hard disk, find this, load it into memory, and do all sorts of things. And that's going to take time. So we have to wait for it to be started. 3 seconds in computer time is, it feels like anyways, an eternity. But if you have a low-end device, I'm talking like low-end Raspberry Pi that's got a very slow drive attached to it, that may take a while to load up, especially if it's a large application. So you may have to tweak that. So if we're unable to start it, we're going to return false. So just hit the eject button and jump right out of here. From there, I'm just going to make some code, or I should say make some data that we're going to compress. We're going to say qbyte array for I equals 0 to less than 100, increment, and we're going to say item, and then the qstring representation data append in UTF-8. Very simple. We're just making some junk data that we want to compress. Now we're going to take our process, and we want to go ahead and write to that process. And we're going to write our qbyte array, our data. If we highlight this, hit F1, and it just says it writes, but it doesn't really tell us how it writes it. This is under the hood, I believe, using standard input. So we're basically telling it, use the standard input, here's your data. You'll run into all sorts of problems because sometimes things will want like a /r/n or a new line basically at the end of it. So you'll run into those kind of issues. Once we've written the data, I'm going to say gzip dot, and we want to close the write channel. What that does is it says we're no longer going to be writing this. Now, if not, gzip dot wait for finished. And of course you can and probably should give that a timeout. We're going to go ahead and return false. And this does exactly what you think it would. It's going to sit there and wait for gzip, the actual application we're calling, to crunch numbers, do what it's going to do, but we want to time this out after a certain amount of time. If it never finishes, meaning if it's just running and running and running, I'm sure you've seen applications do that, we want to just go ahead and return, get rid of it. There's probably more cleanup you should do there. We're still in the infancy level of our understanding of QProcess. And then we're going to say qbyte array result. We're going to say gzip. And we're going to go ahead and read all, meaning we're going to read all of the output from the actual application on the standard out. You can highlight this and hit read all. Reads all remaining data, blah, 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 blah. Notice what's going on here is that it's just going to simply return it as a byte array. The function has no way of reporting errors. Very important you understand that. Each application is going to report errors in their own subtle way. You may get nothing back. You may get back some sort of weird error code, or it may actually say error unable to process. Every application is going to be different, unfortunately. And then to wrap this up, I'm just going to qinfo some stuff out. We're going to say before, and then we got our result. We're going to say the result size and the compressed version. Let's go ahead and save and run this and see what this looks like here. Ta-da! So now we've got gzip compression that we can use as long as gzip's installed on the system. Here's our data before, here's the result, and here is the compressed data in all of its glory. Again, it seems overly simple, and it is by design, but there's a billion things that can go wrong, and I guarantee you this will frustrate you. Some of the things that'll frustrate you is if it's not available on the system environmental path, you'll have to give it the full path name, and sometimes an application just won't start. You'll sit here and wait for started, and it just seems like nothing happens, and you're trying to figure out why. And it's because usually the application needs a certain environment set up for it to run. You'll run into that constantly, and it'll drive you absolutely bonkers. Unfortunately, all I can tell you is see that application's documentation for the appropriate way to run it. Then write, sometimes you'll find that you'll write and nothing happens. And it's usually because at the end of this, you'll have to do like a /r/n kind of thing to tell it like, hey, the user hit enter on the keyboard. Close down that write channel and then go ahead and wait for it to finish. Go ahead and read it all back. Now remember, read all has no way of reporting errors. It's just going to read back whatever the process is spitting out into the standard output. That, in a nutshell, is the high-level version of how to use QProcess. One question I'm always asked is, since read all has no way of getting an error code, how do we actually determine what happened? And honestly, the code's so short, I just already have it copy and pasted and ready to go. We're going to start a process and get its exit code. Remember, when we run our program, our main function comes in, goes into an event loop, does something, and then returns an exit code from our QCore application.exec. 0 is a good thing. It means no errors, but you can absolutely return an error code back. And all processes do the same thing. So when working with QProcess, the process itself will have an exit code. Let's go ahead and demonstrate that. Real quick, we start our app, we go into an event loop, we start a process. In this case, I'm going to use Z. Z is just simply a text editor. If I go ahead and do this, you'll see, ta-da, it's the text editor we've been working with this whole time. But feel free to do like notepad.exe or something like that. So what I'm going to do is say Z and then open up this website, which is actually my website, voidrums.com. Some programs won't do that. Like I'm not sure if you use notepad.exe or anything like that, if it's going to actually try to load the URL, but Z does that just fine. Once I close Z, it will issue an exit code back to the operating system. Let's go ahead, save, run, and see this in action. So there's Z, it's downloading the code from my website right there. There's the HTML. And if we look here, you see how it's just sitting here, it's starting. And it's because it's waiting for Z to finish. Now I'm gonna close this and exit code 0. So Z, the application, closed without any problem. So in case you're ever curious and you get some weird kind of crazy output from a process, check the exit code and see what it says. If it's something other than 0, there's a problem, and unfortunately, you'll have to look at that documentation for that application. This video may hurt your brain if you're a newbie. Notice I have highlighted, show we have the full system available. It's a little bit misleading. What we're going to do is process custom commands. And the reason why this is misleading is because your application is going to run with the permissions of the account running it. Meaning if you try to do something and you need administrative control over the machine, your application needs to be run as an administrator. Okay, what we're going to do here is we're going to almost simulate, or more to the point, interact with a command line. On Windows, it's CMD. Most Linux, it's Bash. And on Mac, I think it's ZSH. At least it was on my MacBook Pro sitting right next to me here. So we have this glorious main function that has absolutely nothing in it, along with this very generic QObject I've not filled out yet. In here, we've got QDebug, QProcess, and QSysInfo. Not sure if I'm going to use QSysInfo. I'm going to kind of freestyle this video a little bit here. What I want to do is automatically, right off the bat, we want a deconstructor. So I'm going to say Commander, bang. And I'm just going to refactor and add definition. Now I'm going to skip over signals. I'm going to say public slots. And I want void ready read. And then void action. So ready read, we're going to connect with QProcess's ready read signal. Action is kind of our own. I'm going to say Q byte array data. This is going to be what we want to do on that command line. I'm going to say private, and it does bug some people that I put a private section down here, but I just really want to split it up. QProcess, let's call this proc, and then QString, app, and QString, and L. Yes, I'm going to kind of do some things you probably wouldn't normally do. For example, normally you wouldn't define your own int L. I'm just showing you can do it. Let's go ahead and flesh these out. All right, now we need to actually implement, and there's going to be some copy and pasting going on here. So first things first, let's go ahead and do QSysInfo, and then we have, by default, I'm going to use bash, and then our indel is going to be a /n. If it's Windows, then do cmd with /r/n. For Mac, it's going to be zsh with a /n for an inline. Basically just showing you that we can take complete control of this if we want. Now, what we want to do from here is we want to proc.setProgram. And this is going to be our app. We're doing this because we already have an instance of QProcess, and now we want to say, hey, use this program as the process we're going to work with. And then, of course, proc.start. We're just going to start this up, and we're going to start it with no additional arguments. Now, from here, we have to do some connections, and I absolutely hate doing signal and slot connections. They're super simple, but here they are. Let's just plop them in. I'll probably have to do a little bit of surgery here. Yep. I had a rough idea of what I wanted to do, and of course I didn't have case sensitivity in mind when I was jamming that out on a notepad off the screen here. So we're going to connect our processes QProcess ready read to our classes ready read. So when the process has some data available, we're going to go ahead and try and read it. When the process has a ready read standard output, we're going to say, hey, go ahead and read it. When it has a standard error, go ahead and read it. So you notice all of these are going to our ready read. Very, very simple. We're going to do all the work right here. Now in our deconstructor, this is where I'm going to say, hey, if we're still running that process, proc.isOpen, let's go ahead and say proc.close, meaning we don't want that thing just hanging out there. Ready read, this is where we're going to say, all right, we got some data. We want to read that data. I'm going to say qint64, because we don't know how much data we're going to be getting here. I'm going to say do while the value is greater than 0. Inside our little do loop here, this is where the fun really happens. This is a party in a scope is what I like to call it. So we're going to say qbyte array. That was my inner nerd really coming out. Now, somebody out there is going to be thinking of this in terms of a file and say, isn't it dangerous to do read all? Couldn't we be consuming way too much memory? Not really, because if the application is going to pump so much out, it's going to get fragmented in its write, meaning it won't be able to write out gigs and gigs of data. It would just simply crash before it had a chance to do that. So I have to preface, most applications are going to write like one line at a time or a chunk at a time. Some of them out there do some weird things. You wouldn't believe some of the things I've seen. I want to say line dot rims. So really all we're doing is we're grabbing a line and then trimming it. There's different ways of doing this. I'm just showing you a simple way. We say value equals the line dot length. I'm doing this because sometimes programs misbehave and they'll pump out like 30, 40, 50, even 60 blank spaces. Why? I don't know. People do weird things when they write programs. I'm sure there's a logic for it. Maybe they're just trying to make the console interactive or fun. I don't know. But basically, we're going to read the line, remove any white space, and then get the length. And if the length is greater than 0, we're just going to keep looping. So if they send us a blank line, we're done reading. Again, you'll have to tweak this for your own means here. What we want to do next is we want to take action. And we're going to say if not data dot ends with, work with me here, keyboard, ends with, and we want our end L to Latin 1. We're just working with ASCII. You can do this a billion different ways. And I'm just kind of mixing and matching just to show you can. Probably not the best idea, but we're going to go ahead and append our end L dot to UTF-8. Again, probably not the best idea to mix and match those, I'll admit. Now I'm going to say proc dot write. We're going to go ahead and write this to the actual process. And then, of course, proc dot wait for bytes written. It's actually pretty important that you do this. What I've seen happen is that you'll put proc write in a function like this, and the function will exit, and it just doesn't have time to write that. So you really should wait for bytes to written before you do anything else, because if you start hammering that process with too many actions at once, it's going to get really confused. You may have like multiple commands mingling with each other, and you'll get some just bizarre output in your ready read. You just want to be a little careful, I guess, is what I'm trying to really get. Now, from here, it actually becomes pretty straightforward. We're going to jump over to our main, but let's give it a good build just in case. Want to make sure we don't have any little gremlins waiting for us. All right, let's go ahead and make an instance of our commander. And then I want to say cmd.action, and we want a q byte array. Again, there's a billion different ways you can do this. And we're just going to issue something to the application. And in this case, I'm going to say PWD, which stands for print working directory. This is the same as me opening a console and typing PWD and hitting enter. We should see where we're at in the application's directory, meaning where are we currently running inside the operating system. Then I'm going to grab this, and let's just do something a little bit different. Let's say like ls-l. If you don't know what ls-l is, like if you're a Windows person, it's basically going in here and saying list like this, and it's going to just display our directory with our permissions, the group, user, bytes, date, time, and then the name. Windows folks, you may be going, wait a minute, I think most modern Windows systems will run this. It did on my Windows box, but admittedly, I'm not sure if I had done something that made it do that. Usually when I'm in Windows, I'm playing video games. So you can 100% tweak these commands for your operating system. So you could say like a dir, or you could say, lister, whatever you wanted to do, whatever is specific to your OS. Point being, if we're running Windows, we're running command.exe. Linux is going to run bash, and Mac is going to run zsh. You can tweak that as you need. Let's go ahead and save run and see this in action here. Ta-da! So here is the directory the application got back from bash. And here is and you notice it's all kind of jumbled up here. The response we got back from our ls.l. And you notice right here, these double empties. So this is what I mean by you cannot always expect that it's going to behave well. Let's go ahead and explore our process's life cycle because we are a process. Our application that we're working becomes a process when it's run. So we have our Q-Core application, we have a Q timer, which basically waits a certain amount of time and then does something. So from here, I'm going to say Q info, and we want to know what arguments were given to us. And I'm going to say, we want to know up to this number, our argc. And the operating system's handing us an array here. So let's go ahead and grab that. And we want to know that specific element in the array. It's just going to simply print it out. Now from here, I'm going to say Q timer. Single shot. Whoops, got that a little screwed up. Single shot. And what this is going to do is it's going to trigger once and only once. And we're going to do this in 3 seconds. And now we need an object or a receiver. That's right. This is signals and slots. So what are we sending this to? Well, we want to send this to our application, Q-Core application, this little A here. So let's go ahead and say A. And then we want to call a receiver here. Now, what I want to do is something a little different. I'm just going to say slot. This is the old way of doing it in Qt. And we can define the slot we're going to call. We highlight Q-Core application, hit F1, and kind of go down here. You can see the public slots is quit. And going into quit, ask the application to quit. Notice it doesn't force it. It simply says, pretty please stop what you're doing and exit. You ever have a hung process? We're hoping that this little application wouldn't become hung, but it very much could happen. So just bear that in mind. Now I'm going to do a little bit of surgery on this. I'm going to get rid of this guy. I'm going to say int code equals, and we want to get the exit code. We've done this before very sparingly, and I'm going to say code and print that out. Now we want to actually be nice to the OS and return that code back to the OS. So what we're really doing here is we're intercepting that, and we're saying we want to see the application's full life cycle. So our app's going to start, we're going to run some code, and then we're going to go into an event loop. Timer then is, notice how I backed up, we're going to enter an event loop, and then the timer, 3 seconds later, is going to call quit on our application. This will exit and give us a code, which we'll print out. Save run, and let's see this in action. All right, so it did give us some arguments. That's how we know where we were, and boom, exit code 0. Notice how it says return. Somebody's going to go, oh, your application crashed. No, actually it didn't. We quit it. We called the slot quit. To kind of demonstrate that, let's go ahead and move this out to 6 seconds. Save run. And as soon as this runs, that timer kicks off. So in about 4 more seconds, it's going to actually stop our application. There we go. This is actually pretty cool. We now have complete control over our own application and our application's life cycle. This section is going to be a primer on threading. Now, threading is an advanced topic that I'm going to cover in the advanced course. That's why I'm saying this is a primer. Don't expect to be a threading expert because, let's just face it, it's very complex. If you're not sure what a thread is, your application can run on multiple threads within the CPU, meaning you can do multiple things at the same time. For example, if you ever talked on the phone and cooked dinner, that's an example of multi-threading. The simplest of this is a timer, and we've already seen this, but let's look at it again. So we're going to make a Q timer and do single shot. I'm going to say void test, and let's go ahead and say Q info. Thank you for waiting. Now, this seems overly simple, but this is just really confusing in some application frameworks. So let's go ahead and Q info, and I'm going to say, please wait. Now, what you're going to see in a lot of forums is how do I make my application wait? And they're going to call sleep. If you do that, you're putting your main thread or your application itself to sleep, and you don't want that. So this is just going to introduce a timeout. So I'm going to say Q timer, single shot, meaning we're going to wait, and then one time and one time only, we're going to do something. And I'm going to wait 5 seconds. And then I'm going to call a function. We're going to call that test function. This is actually fairly complex under the hood. This little application, you wouldn't know it. So looking at this, what we're doing is we have an application. We're going to start a timer, and then this is going to run in a separate thread altogether for 5 seconds, and then it's going to wake up and come back to this thread and call this, even while we're sitting in an event loop churning around waiting on our application to do its thing. Let's go ahead and dive in and see it in action. So now it's sitting there and the timer is running on a separate thread, and it'll wake up and then it will say, bang, thank you for waiting. That's an example, a very simple example of multi-threading. If you don't really understand the concept yet, but without diving into the computer science, your computer is capable of doing multiple things at once. So you can leverage the full power of your computer. For example, there's a concept called cores, and let me bring up, and this is on my main box here, not on the virtual machine. Whoa, very, very big. Let's just get this down here. My main box has multiple cores. I have 8 cores total. So our application could run and take up all of these cores if we wanted to. That's actually extremely cool. Now on this virtual machine, we have a much scaled down version of that. So this virtual machine has 1, 2, 3, 4 CPUs or 4 cores, even though it only has one virtual CPU. We can still leverage each of these. So while we have a thread running on CPU 1, we can have another thread doing something on CPU 2 and another on 3 and another on 4. This gets very, very complex, and kind of have respect for what you're doing. Qt makes it simple, but again, this section is simply a primer. We're going to cover this in the advanced course in detail. Looking at the previous example, you're probably inclined to believe that a Q timer can be used once and only once. It's completely wrong. Q timers are meant for intervals, and let me go ahead and explain this. We want to wait without blocking execution of our application, but we want to do something at a certain set interval. Think of it like a stopwatch almost. To do this, let's go ahead and make a class. We've got test.h. In here, I've got QDebug, QTimer, and QTime. Don't confuse timer with time. The timer deals with threading, and time deals with date and times. All right, now what we're going to do here is we're going to say public slots, meaning we are making slots in our class that are going to be available to the outside world. We want timeout. And then void do stuff. And of course, do stuff will just simply, well, do stuff. And let's go ahead and make a private section here. We want our timer. And then a number. So let's go ahead and flesh this out. We're going to make this very, very simple. Add definition. And then add definition. Now, I've done this in a specific manner, and I want you to kind of understand this. So in our constructor, we need to actually set up the signals and slots. So I'm going to say number equals 0, timer. We want to set the interval. That means we're telling this how often this should emit the signal that calls our slot. Every second is what I'm going to set this to. Then we're going to connect the signals and slots together. And I'm going to connect, and I absolutely hate writing connect code, but I'm going to do it. So we're going to connect our timer to the Q timer, and we want the timeout. So every time timeout is called, it's going to call this object, which of course is a test. It's going to call our timeout slot. So looking at this code, every second, as long as this timer is running, it's going to fire off our timeout, and then we need to actually do something. So I'm going to say number. Go ahead and increment that. And then let's say Q info. This is where we're going to say Q time. We want the current time. Let's go ahead and do this on a toString, and I want the Qt date format text date. If you're coming from Qt 5, note that's very different. The Qt 5, let me copy and paste it. It's going to look like this, where you're going to say system local long date. Qt 6, that's changed to text date. But then I want to do some special processing because I don't want this to go on forever and ever and ever. So I'm going to say if the number is equal 5, or you can say greater than or equal to 5, just in case you're paranoid like me. You can say timer.stop. Now we're going to tell the timer stop. Just like a stopwatch, we're clicking that little stop button. I'm going to say QInfo complete. All right, now our do stuff. This is where we're going to say, hey, let's go ahead and say timer. Go ahead and start doing some stuff on other thread. And we're going to go ahead and start right there. Very simple, very easy to use. So basically the outside world is going to say, hey, do stuff, and we're going to start our timer. As that timer churns away, every time it times out, it's going to call our timeout function. We're going to count. If we get to 5, we're going to go ahead and stop that timer. We could, if we wanted to, make this reusable by simply setting that number to 0 every time do stuff is called. From here, let's go into our main, and it becomes very, very simple. You're going to be surprised how many applications actually use timers under the hood. And we're going to say do stuff. Save, run, and let's see this in action. And every second, it's going to simply print the timeout on the screen. And it is not locking our application up. It's running on a separate thread, but calling the slot in our current thread. Now, if you're a newbie, you may be struggling to go, I want a really good example of why I would even need to use a timer. Well, we're going to watch a directory for changes, and we're going to use what's called the Q file system watcher. What this does is you point it at a directory, and it monitors that directory for changes. And if something changes, it lets you know. You ever seen an application do that where it says, please update the file, you update it, click save, close, and then boom, the application magically knows the file's ready. This is exactly what we're doing here. So to pull off this magic, I have a class called Watcher already filled in, where we've got the Q file system watcher as FSW, and we've got 2 slots, file changed and directory changed. In case you're wondering how I knew how to magically do those, you just always F1 onto the class, go down to whatever signals you want to monitor, and you can just simply copy and paste those into your code. You can see file changed, directory changed. Switching to the source, you see I have not implemented this yet, so let's go ahead and do that. I'm going to, just so you don't have to watch me do a bunch of what I call plumbing code, paste some stuff in there. So we're going to say File System Watcher, add our current path, and then let's go ahead and add our current path with the separator test.txt. That gives you, we're going to be watching the current path and we're going to be watching for a specific file. And then we're going to connect our signals and slots. So we're simply connecting the File System Watcher file change directory change to our classes file change directory change, which are these two down here. It becomes pretty simple from here. I'm going to just do the old copy and paste for the first one. File change, and then let's walk through the rest of this. So we're going to say File System Watcher dot files, and it's going to give us a QString list. So I'm going to say if it's got some in there, let's go ahead and do this and say QInfo. Oh, keyboard got away from me here. It's like I was typing and the keyboard shifted slightly and just messed me all up. So let's go ahead and say QInfo files that have changed. I just want to simply see them. We're going to say for each QString file in our File System Watcher dot files. Let's go ahead and QInfo that out and say our file. Very simple, very easy to understand. I absolutely love how simple Qt makes some of these things. Now from there, we can, well, pretty much take the same code and just kind of grab it. And let's say directory changed. There that have changed, and then let's go ahead and say dir and dir. And then let's go ahead and change this to directories. Very simple, very easy to understand API. Now, what this is going to do, as soon as we create an instance of this class, we're going to instantly start monitoring for the directory and for a specific file name. And then the Q File System Watcher in the background has a timer that's going to continually monitor, and it's going to watch for changes, and it's going to let us know. Let's go ahead and kill that, and let's go ahead and say Watcher. And that's it. We really don't have anything else we have to do. Let's go ahead and save run. All right, so here's our little console here, and we're in 15.3. So let's go out to our file system code, and I've got just a graveyard of code here. Here's 15.3. And there is our little terminal. I'm going to try and get these next to each other so we can see them. Screen real estate's a bit limited on this virtual machine. I apologize. So I'm going to go here. I'm going to create a new document. And you can see in real time as I'm doing this, our little console app is letting us know things have changed. And I'm going to open up our text editor. Hit save in the text editor. And you can see our console's picking up all those changes in the background. This is extremely cool, and it's so powerful. Let's round out this section by taking another look at QProcess. So we want to use QProcess and QTimer, meaning we want to start a process, but we want to kill that process after a certain amount of time. So let's go ahead and flesh this code out. QProcess proc, and we've done this before. We know that QProcess is ridiculously simple to work with. So I'm going to say proc.start, and then feel free to start any application you want. The main thing is that it should let you know when it's closing. So I'm going to use a visual application, in this case, my little text editor, Zed. Feel free to use Notepad, calculator, whatever you want, just to have something on the screen so you can see it actually running. Now, QTimer, we're going to say single shot. And then we're going to go ahead and say proc Now we're going to go ahead and terminate. You got to be a little bit careful when you're doing this. So what we're saying is timer, single shot, meaning do it one time only in 3 seconds. We're going to call our process, this cute process, we're going to call terminate. And this is where you have to be a little bit careful. Attempts to terminate the process. We are not politely asking this to shut down. We're saying, hey, stop what you're doing immediately. Now, console applications on Windows that do not run an event loop or whose event loop does not handle the WM close message can only be terminated by calling kill. So what I'm getting at here is there's different levels of doing this. There's quit, terminate, and kill. And kill is brutal. It kills the current process, causing it to exit immediately, meaning we are in no way, shape, or form completely like a horror movie. We're killing it. I mean, we're coming in with an axe, just smashing it in the head till it goes away. You have to be careful doing this because this could cause data corruption, which is why I use terminate instead of kill. Terminate means, hey, I'm done asking, you're going to shut down immediately. And the application goes, oh, I'm sorry. And it tries to close as fast as it can, where kill is just going to, you guessed it, kill it. Now, I know I said this is a primer on threads, and we're going to cover threads a little bit more in the next section. However, this has been very focused on timers, and there's a subtle difference here. Sometimes a timer will use what's called an asynchronous code. And asynchronous basically means it runs on the same thread, but in a different manner. It uses kind of like the space between execution, and there's a lot of computer science, and I'm explaining it badly, but asynchronous will try to run in the current thread, where a thread will run in a separate thread altogether. Very confusing unless you're a computer science major, but us mere developers, we just want to know that this runs without blocking the execution of our code. So let's go ahead and do this. All right, so it starts my little notepad here, and then it closed it. Did you catch it? I'm going to do it this time without moving it, so there's no mistaking what's happening here. It closes it for us after a certain timeout. That's actually pretty cool and pretty powerful that you can combine these two together, because now even if a process is not behaving, you can say, I don't care, I'm going to kill it after a certain amount of time. All right, this section is going to really hurt your brain. This is where we take the training wheels off and we talk about asynchronous versus threading, and we're going to really focus on threading. Now, again, this is still a primer for threading. I cover threading completely in the advanced course. Remember in the last section, I said the asynchronous code will run in the spaces between on a thread, where a thread is a completely separate thread. This is what a timer really looks like. You'll have a process with async, 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 which all runs on the same thread, which does something on a CPU core. The reason for that is threads are expensive. You're talking about expensive in terms of computing power. There's only so many threads you're going to be able to create. And let's face it, your thread's not always doing something, especially in terms of a timer. It's just sitting there waiting. So if you go out and you Google something like does QTimer run in a separate thread? If so, what's the mechanism? You're going to find that events are delivered asynchronously by the OS, which is why they appear there's something else going on, but not in your program. Basically, it's an async callback to the OS. That being said, I have used the term threading to get you in the mindset that you can do multiple things at once, but this is really what's going on here. Now we're going to depart from that and use actual threading. This is going to be a little bit more cumbersome and a little bit harder to understand. Again, this is an advanced topic. I only added this in to really get you ready for the advanced course. Let's take a deeper look at asynchronous versus threading super quick. So we have this basic model here where we have a process, async calls that run on a thread. Somebody out there is going to say, I still don't understand. Isn't async and thread the same thing? No, they're absolutely not. So asynchronous calls run in the dead space when a thread's not busy, which actually makes it busy. And a thread is a thread or a context running inside of a CPU or a core inside of a CPU. A thread's very expensive because it has a slice of time inside of the CPU. And you can, if you wanted to, do something like this. Let's grab something. And let's just try and line that up a little better. We can say something like this, and then something like that. So now we have multiple threads, and we could potentially even use multiple cores, and we can have asynchronous tasks running on both threads. This is just how complex this can get. And you can have threads calling threads who are waiting on threads, who are exchanging information and creating all sorts of chaos and problems that we need, as the developer, now have to deal with. Before we continue on, I want to really stress this. Threads are advanced, so if you're really struggling with this, it might be a little bit too soon, because this is really an advanced topic, and that's why I cover it in the advanced course. They are prone to mistakes. You're going to have things like race conditions, where you have multiple threads competing against each other, and then one kills the other. You're going to have deadlocks, where they try to access the same information at the same time, and even data corruption. I mean, imagine two threads trying to update the same variable at the same time. Which one's correct? You'll have errors that are just mind-boggling to understand. They may crash your application. We're going to use basic examples only. Remember, this is a primer for the advanced. I know I sound like a broken record, but somebody out there is going to take this course and say, well, I'm trying to build this multi-threaded TCP server that uses multiprocessing to create my own version of AI. That's not what we're covering in this course. We want to go over the basics. Okay, so we have process 1, process 2. Each process can have its own threads, which of course owns part of the CPU state, or I should say uses part of the CPU state. The CPU scheduler inside the operating system tries to translate that to where it should go in memory and on the CPU cores. This is what we're doing. That graphic hits it beautifully. That's how complex this delicate dance is. So if you're like me, you want to see the code running. Let's go ahead and look at threads, and let's understand how this is working. So we've included QThread. I absolutely love QThread. It's one of my favorite classes. So I'm going to try and not talk your head off about this. We're going to say QThread. We're going to say a pointer to a thread. The reason why I love QThread is it's so, I mean, compared to other things out there, it's so simple to work with. We're going to say QThread, and we want to get the current thread. If you start down the path of user interface or UI programming, you're going to hear the term the main thread. That's the thread that our application's actually running on. Now, if we stop this thread, our application stops. That's why you want to use multiple threads to begin with. So let's go ahead, and we're going to get a pointer to the current thread, or the main thread here. Now that we have our thread, let's go ahead and say thread.setObjectName. And let's call this the main thread. That way, when we're in console land, it's very easy to see what's going on there. Now that we have that named, let's go ahead and say, hey, QInfo starting. A little bit misleading here, because the thread's actually already started, but and then from here we're going to say for int I equals 0, I is less than 10. And then let's go ahead and say QInfo. We're just going to print something out here. We're going to say I on our current thread. And then let's go ahead and say QInfo finished. And let's go ahead and put our thread out there again, just so we can see what's going on here. If you look at this, you may be inclined to say, we're not using threads. We're not really threading, and you're absolutely correct. I'm showing you that we can interact with our current thread. And actually, all the code running is going to run on this main thread, because it's our current thread. So that's right. It's going to say starting main thread, and then I on main thread, and it's going to do that a few times, and it's going to say finished. So let's go ahead and see it in action here. This is a good representation of what your code looks like when you're threading. Is you have a thread, so we've started on our main thread, and then this loop is occurring on the same thread over and over and over again. So if this were to block or stop at some point, it's going to lock up our entire application. Eventually we get down to finished, and there's our main thread right there. Unfortunately, as easy as QThread is to use, it's also the source of a huge debate, but I'm going to show you how to run another thread. Why? Because we have this powerful computer, let's use it to its full extent. We're going to use QThread move to thread, and I'm going to show you why there's a debate. Some people think you should use move to thread, and some people think you should actually inherit QThread and use it, which is inherently bad. You really shouldn't do that. Instead, use move to thread. There's a reason for that. You could potentially break that thread if something else inherits it. So I have absolutely no code written. Let's go ahead and flesh this out. And I want to do this step by step just so you can really wrap your head around it. So I'm going to make a class. Let's call this task. And this is going to be something we're going to use in another thread. It's simply going to be a Q object. There's no magic happening here. Let's go ahead and add this. Now we have our task class here. I'm going to go ahead and I'm going to paste QThread and QDebug. And all we want to do is we want a constructor, a deconstructor. Let's go ahead and make a public slot. Well, let's simply call this work. And let's go ahead and flesh this out. So far, we're not doing anything super special, so you may be a little bit bored here, but I'm trying to go through this very slowly, very methodically, so we get our head around the whole process. Now in our constructor, I'm going to say constructed this on, and then QThread the current thread. Because we saw this in the previous video, you're inclined to say, we're running on the main thread. No, this could be running on a separate thread, which is what we're going to do in this video. So we want to know which thread we're actually running on. And then deconstructed on whichever thread. Now comes the work part. So I'm going to say QThread. And this is going to be called thread. Maybe if I could actually spell thread. On QThread, sometimes I get super excited to do these videos and it doesn't help me at all when I'm trying to type. So we're going to say get that current thread. Now we have a raw pointer. Let's go ahead and do something with it. So I'm going to say QInfo. And we're going to go ahead and start. And then we want to say for int I equals 0. Again, I get super excited, and then it just betrays me. And then I is less than 10. You notice some similarities to the code from the previous videos. We're really not deviating a whole lot, and that's why I love this, because it works across every thread we do. Then I'm going to say finished on our thread. Notice what we're not doing. We're not taking care of this pointer. So this thing's just going to work as expected, but this is kind of like our test class where we have a constructed, deconstructed, and then some little helper function that's going to demonstrate something. Really not super powerful here, right? So let's give that a build, just make sure I didn't goof anything up here. And now comes the actual complexity part here. So I'm going to do a few things. I'm going to first grab some includes that we need. QThread, QDebug, QScope pointer, and our task. Yes, so we're going to actually take ownership of this thing. Now, the problem with pointers and threads is you cannot set a parent-child relationship when you're using this, or it'll say cross-thread operation and won't let you run. It's kind of a bummer, but that's just the way it works. And then we're going to say QThread current thread set object name. So we're setting our main as the main thread. Now we're going to actually make another thread. We're going to create a thread. I'm going to say QThread, and let's call this worker. And I'm going to say worker.set object name. Notice this is a Q object, so we can do this. And we're going to call that our worker thread. And then let's go ahead and say Q info. Starting work. And we're going to start this on our Q thread current thread. So I'm just kind of showing you in the console, hey, the main thread is going to start the worker thread here. This is where things get a little bit cumbersome. We need to say something like task equals new task, and voila, but then you're going to panic and say, okay, we want this to have a parent, but if we try to do that and then move it to a thread, we're going to have a bad time. It's going to simply say, can't do that. So we need to find an alternate means of doing that, and QScope pointer or QShared pointer, absolutely beautiful for this. So I'm going to say QScope pointer. And we're going to make our new task here. And this will, of course, auto delete. Now, notice what we're doing here. We're using a scope pointer. So once this function goes out of scope, it's going to kill that pointer. Be a little bit careful if you're trying to use that in some custom code here. You'd want to switch over to QShared pointer if you're moving it to a function. Now I want to say task. Now we want to take that pointer, that task, and do a move to thread. And then we're going to simply hand it the worker. So it's really not QThread move to object. Under the hood, it's QObject move to thread. So what this does is it takes that pointer and simply says, go over to this other thread. We haven't actually done anything yet. This is the confusing bit. So if I run this, it's going to look like nothing's happening. See? You see starting work on constructed, but then nothing happens. So now that we've moved that to the thread, that thread, the worker, is just sitting there doing nothing. So we want to connect up some signals and slots. So I'm going to say worker connect. Let's go ahead and connect our worker. We want the QThread started. And we're going to put that over to our task. And we want to do that to the task work. Now, if it's not abundantly obvious what we're doing here, let's walk through it super quick before I get rid of that little typo. So we're taking a QScope pointer, we're making a new task, we're getting a pointer to that task in the QScope pointer data. So we have a pointer to the task, and then we're saying our worker QThread, when it started, we're going to call that task work function. This guy right here. So it's going to actually print out current thread, and the current thread is going to be the thread that we're executing on, not necessarily the main thread. Now that we have that, we're going to say worker.start. And you see this priority and you instantly get excited and say, I want to be the highest priority. Don't do that. Really don't. Let the CPU scheduler figure out what it's supposed to do and take care of it for you. Just because you're asking for a priority doesn't necessarily mean you're going to get it. Then I'm saying free to do other things, QThread.currentThread. This is it right here. This is about as complex as you really want to go. So there are a whole host of other things that we'll cover in the advanced course, but really what we're doing is we're making a thread. we're adding something to that thread, and then we're going to start the thread. And because we've connected signals and slots, as soon as the thread starts, it's going to go ahead and start our object. This is the beautiful part about QObject. Go ahead, save and run. Ta-da! So starting work on our main thread, constructed a task object on our main thread. We are now free to do other things. Wait, what? Free to do other things. That was the very end of our app. So what happened was all of this thread stuff starts up on a different thread. Or I should say this starts on a different thread. We're free to do other things on our main thread. Main thread is now free to do whatever it wants to do. And we can actually execute code now out on a worker thread. So we have a separate thread altogether that's doing our little bidding. I almost wanted to call that minion instead of worker thread. Now, I'm going to put a note in here simply because somebody's asked in the past, how do I know when that thread's finished? You'd simply connect a signal slot to QThread finished, and you'll know when the thread is actually done. When in doubt, remember that the help system is absolutely amazing. F1, and you have all the information right at your fingertips. This threading stuff is super exciting and powerful, and immediately someone's going to go, hey, I want to run this on more than one thread. So I'm going to create a bunch of threads. I'll make a queue list, fill it with threads, and use that. Don't do that. There's a better way. It's called the queue thread pool. And what this does is it has a pool or a list of threads, and it takes care of all that complexity for you. It's already baked right into your application. This is the coolest thing ever. So queue thread pool, absolutely amazing. It is a class that manages a collection of queue threads, meaning you can have more than one. And it manages and recycles individual QThread objects to reduce thread creation costs in the program that use threads. Each application has one global QThread pool object already accessible to it. To use one of the thread pool threads, subclass the QRunnable. This is where people get really confused really fast, meaning we have to take this QRunnable thingy and make it part of our class. Wait, what? All right, so let's jump over here, and we have our task from the previous video, which just simply was a queue object, and of course, had a slot called work. What we're going to do here is we're going to simply include QRunnable. We're going to then go ahead and say public QRunnable. Now, there's something you should know about QRunnable right off the bat, and this is a source of a lot of frustration for people. If you click this, go to F1, you'll notice it is not a queue object. So then people instantly go, wait a minute, how can I have a QRunnable and still have signals and slots? Multiple inheritance, you're going to use QObject and QRunnable. Then you can just right-click this, refractor, and when I say right-click this, it's QRunnable. Right-click, refractor, insert virtual functions of base classes, and you want to make sure run is selected. Hit OK, and voila. If you want, you could really pretty this up, get rid of that. So what's going to happen is when we run our runnable, I love saying that, run our runnable, in the thread pool, it's going to call the run function. So we can safely get rid of this altogether. Let's go ahead and switch to our source, and let's rename this to run. And get rid of that little guy. Now we have a runnable that will run on a thread pool that also can use signals and slots because it's a queue object. This, I mean, my mind just gets blown by how powerful that is. Minimal code changes, and we now have all of that functionality. Now we're back at our main. We are going to, you guessed it, we're going to take a thread pool and we're going to work with it here. So we're going to say queue info. And I want to know how many threads we're going to make. So we're going to say max threads. We're going to say queue thread pool. And we want the global instance, the max thread count. So before we even do anything, let's go ahead and save run and see what this is going to look like here. So we're going to have a maximum of 4 threads. Now, if you were paying attention in the timer video, if I go system, we have 4 threads and we have 4 cores. On different systems, you're going to have different cores, which will change the number of threads. And yes, you can change that maximum, but it may not really be beneficial for you to do that. So basically, the thread pool under the hood is going to determine the number of cores you have, or try to, and then figure out a good maximum balance. It's going to try and balance your application for you. Then I'm going to do something like this. For int I equals 0, I is less than 50. I'm going to go ahead and increment I. And we're going to say task. We're going to make a new task here. Now notice what we're not doing. We're not using QScope pointer or QShared pointer or anything like that. Instead, we're going to say task.setAutoDelete to true. This is part of the runnable. We're telling the thread pool, go ahead and delete this when you're done with it because I won't need it anymore. So now the thread pool itself is going to take ownership of this object and do its magic. From here, we're going to say QThreadPool. Want the global instance, and we're going to go ahead and start. And notice it's going to take a QRunnable, which of course is our task. Under the hood, what's going to happen is the thread pool is going to schedule our task, and then when our task is ready to be run, it's going to call this run function, which of course has our code. Let's jump back here and let's save and run and see this in action here. Ta-da! That's a lot. I mean, that's a lot of output from this little app. That's how powerful this is right off the bat here. So we've constructed some tasks on the main thread. QThreadPool is going to use a pooled thread. This is something it manages, and you can see it's starting, and then it's going to construct some more, and it's going to just keep going and doing its thing, and it's going to go and 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 keep on chugging away. It's that powerful, but yet it's that simple. So now you have at your fingertips, baked right into your application, a thread pool that you can command your own army of threads to do your bidding. Now we're going to talk about something that's even a little bit more mind-bending here. We're going to talk about concurrency. And you'll notice right off the bat, it says Qt concurrent file not found. I left that there for a reason. We want to tell Qt, we want to use threading, aka a QThreadPool, but we don't want to worry about any of the complexity that we've discussed so far. We just want to do something and have it run on that thread pool for us. To do that, we need to use Qt concurrent. If we highlight this and hit F1, you'll see Qt concurrent namespace provides high-level APIs that make it possible to write multi-threaded programs using low-level threading without using low-level threading primitives. What, I don't understand. Basically, it means we're going to say, hey, Qt, take a function, throw it in a thread pool, and let me know what happens. But to do this, we have to add concurrent. So if you're on QMake, you'll have to say Qt plus equals concurrent. If you're in CMake, you're going to have to go ahead and add in the concurrent library here. And I'm going to show you how to do that in CMake because that's what I'm using. So this is just the standard CMake. We're going to go in here and I'm going to just simply go to core right here, hit space, and then enter concurrent. And then the same thing for our find package here. Concurrent. And then same thing here again, but I'm going to grab all of this in front, bang. So we're going to say whatever version of Qt you're using, use the concurrent. So we're using core and concurrent. And I know this course is Qt core intermediate, but I also wanted to touch on the concurrency. This is very advanced. So again, this whole thing is just a primer here. Once you get to that point, that should clear up. Give it a good build just to make sure everything's linking properly and working the way it should. All right, good. From there, I am going to just copy and paste a function. And you'll notice this has got threading in it. So we're saying QThread, get the current thread, blah, 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 blah. And we're just running some values here, right? We want to take this and run it in a thread pool, but we don't want to have to worry about the complexities of QRunnable or QThread pool or any of that. We just want to say, hey, go run that function. So we're going to use what's called a future. I'm going to say QFuture, and I'm going to say this is going to be waiting on an int. The concept of a future is pretty challenging. Basically, we're going to do something and we're going to expect something back, a return value. We expect that back in the future, not necessarily right away. So I'm going to say future1. It's kind of like that movie, Back to the Future. And we're going to say Qt concurrent. And then we want to go ahead and call run. And then we're going to say go run this test function. So concurrent, you notice it's Qt concurrent, not Q concurrent. It's going to go off and do all of this code in the background for us and take this function and run it on a thread pool. And we can do this multiple times if we really, really want to. So for example, I'm going to say I'm waiting on 3 things: future1, future2, and future3. So we're going to run this 3 different times. This is going to return a value. We want to get that value sometime in the future. All right, from there, I'm going to simply say QInfo. We're going to do something, and then at some point, I'm going to say, I'm going to go back and see if that value is ready. And then this will actually block our current thread when we say future one.result. So what this is doing, if we hit F1 and look at this, it says returns the first result in the future. If the result is not immediately available, this function will block. Whenever you see the word block in threading, be afraid. It means it's going to stop our main thread and wait on this to finish. So we got to be a little bit careful here. So it's going to hit the brakes and say, hey, if you're not done, I'll wait on you, but you better get done fast. And then we're just going to say we want future 1, future 2, and future 3. We can even name these value 1, value 2, and value 3. Now, looking at our code before we run it, we are going to do some QInfos, and we're going to print out the current thread. So you're going to see what thread that's actually running on. Say run. Let's see this in action. Ta-da! You notice something? It's running on a QThread pool. And there's the pooled thread right there. And it's giving us back our values. This is insanely powerful. Now we have multi-threaded applications without even have to worrying about threading. I absolutely love it. This video is going to cover signals and slots across threads. This in the past was not super obvious why it wouldn't work. They've actually made it super simple. So I'm going to whip through a lot of this code because we don't even need to understand it. If you've been paying attention, you already know all this. So we're going to have 2 objects, a consumer and a producer. They are going to live on 2 different threads, and they're both Q objects. This looks like complex code, but it's really very simple. The producer is going to produce a random value and emit a signal called produce at a specific interval. And when it's done producing, it's going to emit finish to let the outside world know, hey, I'm done producing, go ahead and shut down. It's going to have a slot called start. So when the thread it's running on starts, it will start this producer. And then we have a timer internally we're going to use, which is why we have a private slot. And this timer is going to call this timeout, which is going to actually produce the value. Let's go ahead and switch to the source. You can see it's pretty basic code. We have a count, a max, constructed on whatever the thread is, deconstructed on whatever the thread is. Start, again, called when the thread is started, starting on whatever the thread is, and then we're going to go ahead and make a new timer with a parent-child relationship. I'm doing this here because I want this timer to live on the thread we're running on. Then we're going to connect our signals and slots. So I'm going to say connect our timer timeout, and then we're going to connect our producer finished to the timer stop. So when the producer's done, it's going to stop that timer. Set the interval to ½ a second, and go ahead and start the timer. As this timer ticks away, it's going to call timeout through the connected signal slot right here. This will generate a random number between 1 and 100, And it's going to say we produce whatever value on whatever thread we're running on, and it's going to emit this produce value. That's going to go into Qt Core and say, hey, anything connected to me, let them know via signals and slots that we produce something. Increment our count. If our count is greater than or equal to the max, we're going to go ahead and emit finished, meaning we're going to tell the outside world we're done producing, go ahead and do what you need to do. Consumer, though, this is much, much simpler. Constructed on, deconstructed on, and then consume. This is where we're going to get that value, and we're going to consume that value on whatever thread this is running on. Remember, these are going to live on 2 different threads. Very key that you remember that here. So in our main, we have a cleanup function. I'm just going to demonstrate that you could clean up a different way if you wanted to, because we're going to have some potential memory leaks. We're saying our current thread, set object name, main thread. All right, now that we're at this point, we can actually start writing some code. I wanted to get all that pre-staged so you're not sitting here for half an hour watching me type away. So we're going to make our producer thread. We're going to say pthread. We're going to set the object name. I'm going to set that to producer thread. Now I need to go ahead and make an instance of our producer. So I'm going to say producer pointer equal new producer. And this is where you got to be a little bit careful here. Remember, if we try to move that to a thread and it's got a parent, it's not going to work. So let's go ahead and say producer, move to thread, and let's move that to our parent thread. What have we done here? Oh my gosh. So we have actually created a memory leak. If we run it like this, it works. It does actually move it to that thread. See, constructed, but then of course it's not deconstructed. There's our memory leak. And if we try to set this parent, so for example, I'm going to set the parent as our Qt Core application, you're going to get this error message instead. Move to thread cannot move objects with a parent, meaning bad things are going to happen. You simply can't do that. So that is one of the downfalls of using a parent-child relationship for memory management. I'm going to show you an alternate way called delete later. So anyways, we've got this all set up and ready to go. Now I'm going to just, because I'm a huge fan of copy and paste, I'm going to say QObject connect our pthread, our producer thread, started to our producer start. So when our thread starts, our producer is going to start. And in our producer start, go in there. You can see this is where we're making that timer, and we're going to start producing values, which is going to call on this timeout right here. Pretty simple, pretty easy to understand, but just in case. Now let's go ahead and grab this, and we are going to make our consumer thread. And we're going to make a consumer. So what do we got here now? We've got 2 different threads, a producer thread and a consumer thread with 2 different objects, a producer living on the producer thread and a consumer living on the consumer thread. API is very simple, very easy to understand. Now, this is where the confusing bit comes in. If I say C thread start and then P thread start, notice I'm doing that in a specific order. We want that consumer ready to go before the producer's even loaded, simply because if we start producing values and the consumer's not listening, we're going to start losing values. But if we run this, nothing happens. See, we're producing, but we're not consuming, and it fires off finish. So we have to connect signals and slots. And this is where I am going to just copy and paste an ungodly amount of code here. Let's actually clean that up a bit. So we're going to right click, we're going to toggle indent. That is a lot of connect code. We'd be here for 20 minutes watching me try to type that out. I'm joking, it'd be more like a minute, but seriously, QObject connect, we're going to connect our producers, produce signal, to our consumers, consume. So when we produce something, we're going to consume it. Notice those are on two different threads though. And then we're going to say producer finished. Our producer thread is going to quit. Very simple to understand. When we're done producing, we're going to say, hey, thread quit. Now, down here, we're going to say our producer thread finished to our consumer thread quit. So the producer is going to tell the consumer thread when to quit, and our consumer thread finished is going to call our consumer delete later. This is baked right into QObject, and if we F1 on that, it schedules this object for deletion. That's how we're going to get around that memory leak. That is a slot, so you can do this via signals and slots. It's actually pretty awesome. And it says, note, this is safe to call this function more than once, meaning you can just call it however many times you want. It's just going to try and delete it. If it's already deleted, it's not going to worry about it. And then the same thing for our producer. Once our producer thread is finished, the producer QObject is going to call delete later and schedule that object for deletion. So now we have multiple levels of memory management here. We have parent-child relationship, we have smart pointers, we've got delete later, and we can also do the old C++ way of just calling delete. And then cthread finished, we're going to call our QCore application quit. So we're going to tell our application to actually quit. And then last but not least, we want to say our application, when it's about to quit, we're going to call this cleanup function up here. Wow, that's a whole lot of connection code, but this is the beauty of it. Once you make all those connections, it does that elegant dance in the background and you don't have to worry about it. This is right here, just in case you had some other pointer that was not a QObject that you wanted to clean up, you would actually delete it right here in our cleanup function. Let's go ahead, save and run. Now, this is going to be a little confusing if you're coming from Qt 5 because it magically works. This is awesome. So we're constructed on our main thread, and let me actually. All right, so constructed our producer, constructed our consumer, both on the main thread. And then we start the producer on the producer thread, and then we produce on the producer thread, consume on the consumer thread. So these are two separate threads talking to each other. And it just does what it has to do. And then you notice we've deconstructed our producer and deconstructed our consumer. So now we don't have that nasty little memory leak anymore. And we've called our cleanup code and our application shuts itself down. Again, the big takeaway from this is signals and slots are amazing. I absolutely love them. If you're coming from Qt 5, or if you bump into this problem in the future where this does not work, the signals and slots don't appear to be firing, it's because of the connection type. So let's go ahead and go Qt. The default is an auto connection. And in Qt 5, this would betray us on signals and slots. It 100% would not work, and you're struggling trying to figure out why. And it's because under the hood, it was doing what was called a direct connection, which directly connects between those objects. And you would have to actually do a Qt connection. You would have to set the Qt connection for each and every one of these, like this. If it's on a separate thread, I should say. But they have fixed that in Qt 6. Now, I'm going to say it. Because this is new, I'm not sure if I fully trust it, but it is working. Just if you have that problem where your signals and slots don't seem to be connecting, like you're emitting the signal and the slots never being called, 9 times out of 10, it's because you want to set that connection type to a Qt connection.